Okay, so the last question we're going to do together is this one here, where we have a cart on a table, a mass pulling the cart down, and the cart's going to go to the right and the mass is going to go down. And typically we would do this in class as a lab, but we're going to try and solve this question just on paper. Okay, so this question looks like it's in 2 dimensions. So it means that the motion of the mass goes up and down, whereas the cart goes left and right. So it looks like there's 2 different directions here. But the trick to this type of question is, if you can imagine taking that mass and pulling it up to the right, and the same sort of motion still happens. Essentially what you have is a left and right motion of the cart and the mass together, where the responsible force is the force of gravity pulling on the mass downward here. So let's reread the question. So we have two objects here attached by a string. Frictionless pulley, massless rope. Again, our rope is not going to stretch or break under any tension. And we have the kinetic friction of, the coefficient of kinetic friction is 0.15. Okay, and we've been asked to find the acceleration of the mass cart system, the tension in the rope, and the speed at which it reaches the pulley if it was to let go. Okay, so the way we set this question up is we turn this situation into sort of a left-right situation. So what I like to draw is kind of like this. So we got our cart, and we attach it to our mass, but our mass now is kind of, so the pulley would be somewhere in here in the middle, and our mass would be out and to the right. Okay, our objects will move in this direction, and we'll say that that's the positive direction. And this will help us now, because now when we go to draw our force diagrams, we'll have everything in, one direction, the left and right direction, or the x direction. Okay, so we can still write out our given. So the mass of our cart is 0.8 kilograms. The mass of our, what's it called? Hanging object, let's call that H, is 0.2. And mu k is 0.15. That's all the information that we have. Okay, we're looking for A, we're looking for tension force, and we're looking for V2. We know that the cart starts at rest. Okay, so that's all the information that we know. We don't need to do any other conversions. Okay, so when we go to draw our interaction diagram, I'm thinking the best way to do this is to set this up as a system where it kind of looks like the sleds. So the sleds are lined up on the ice and someone pulls them along. But in this case, something that's pulling them along is gravity, because essentially it's gravity that pulls this mass down and pulls everything along. Okay, so our system is going to be the cart and the mass, or the hanging mass, together. Okay, so what we're going to do is draw that interaction diagram. Now, what we need to be careful of here is that we need to consider the forces that are acting on the system, the whole system. So we have our gravitational force with Earth, and our friction force with the table, and our normal force with the table. Oh, we could have just put that there. Okay. Yeah, and that's that. So from this, we're going to draw our force diagram. And the tricky thing here is to figure out which forces are acting on the system in the direction that we care about. Okay, so we have our gravitational force going to the right. Now that looks weird because we have our mass here, right? We have our mass, and essentially what we've done is we've reoriented it so that it looks like it's being pulled to the right, whereas we know realistically it's being pulled down, but everything's being pulled in that direction. Okay, so FG2 is going to go to the right of our system, and the only thing that's ultimately reacting or opposing this is the kinetic friction force on the cart. Okay, we do have a normal force up and a gravitational force down, and that's the gravitational force of the cart. Okay, I should be calling this FGH for hanging mass and FGC for cart. Okay, we know that the acceleration of the system is to the right according to the way we've drawn our picture. Okay. So that, I think, is the hardest part of this question, is trying to figure out how to draw our system in one direction. Sorry. Okay. So the positive direction will be up and to the right. So I think it'll come out clearer when we write our word description. So the mass cart system accelerates in the positive direction due to the force of gravity on the hanging mass, which is greater than the frictional force on the cart. Okay. Our assumptions, again, same as usual: point particle, constant acceleration, and no stretch in the rope. Okay. All right, so the hard part's done, setting up the question. Now we just have to go with what we usually do. So for our mass cart system, we are looking at the net force equation in that direction. That is Fg2 take away Fk equals the total mass times the acceleration. So what are we looking for? We're looking for A. So it's Fg2 take away Fk all over total mass. Darn it. Sorry. So we're looking at the mass of the hanging mass. That's a lot of masses. Minus mu k Fn. Wow, sorry guys. Need my second coffee, I think. But the normal force here is going to be equal to the gravitational force of the cart, because we know that in that situation, those forces are balanced. Up here, this is for the cart. Okay, so we plug in our information like that. So the hanging mass is 0.2, G is 9.81, mu is 0.15. The force of gravity on the cart is the mass of the cart times G over, that's nice, that's just 1. And so we get the acceleration of the cart being 0.78 meters per second squared. And that's to the right for the cart, and that's down for the mass. Because ultimately we know that the cart's moving to the right and the mass is moving down. Okay? Whew, tricky. Now, we have to find the tension in the rope as per part B. In order to find the tension in the rope, I'm going to draw a new system diagram where I'm just looking at one of the objects, and I'm going to look at the simpler one. I'm going to look at the hanging mass. So the hanging mass has tension upwards and gravity downwards. Okay, and then of course we have our tension upwards and our gravity downwards. They're not equal, one's bigger because we know it's accelerating downwards. Okay, and we know that acceleration, we just found it. Okay, so we're going to use this system to find tension force. So we draw our net force equation in the y direction for the system of the hanging mass. F net y, we're going to say that down is positive, so F net y is FG H minus Ft, and that's equal to the mass of the hanging mass times A. So then Ft, if we rearrange that, it becomes Fg minus Ma. Okay, that's like swapping out these two guys. So then we have the hanging mass times G minus the hanging mass times A. We can factor that out. If you factor that out, you get 9.81 minus 0.78, which is 1.81 newtons. Okay, so our tension force is 1.81 newtons. I'm just going to double check that that's right. 9.81 minus 0.78 times 0.2 is 1.8. Yep. Okay, so that's the tension in the rope. Our last question is asking us for V2. And because we know A and we know delta D, we can find V2. And that is going to equal 0.88 meters per second. Checking sig digs, I've got two sig digs here, here, and here. All right. So we've used lots of things in this question. We've changed two directions into one direction. We've used two different systems to solve two parts of the question. We've used our idea of friction force as well as Newton's second law to solve this problem. And it was quite the problem. It's quite the doozy. This is just like number 3 in your homework. So if you feel like you want to redo it, try that question. And yeah, there's also good examples done in the textbook that those will help you too if you feel a little bit lost at the moment and don't want to watch this video again. Okay? Good luck, everyone.